The last sections in this chapter we need to concentrate on are 3.9 and 3.10. They deal with limiting reagents and reaction yield. Limiting reagent is a very simple concept. Think of what the title means, limiting reagent. Reagent is the same thing as saying reactant. They just, different words, means the same thing. So basically, the limiting reactant or reagent is the one that's used up first in the reaction. And once this reactant is used up, then the reaction stops because you need all of the components to keep going. But once one of them is used up, then the reaction stops. That's basically what this is trying to say. So you have something that's called the limiting reagent, and then you have something that's called the excess reagent, which that's the one that is not used up first. I'm showing you an example here where 2NO plus O2 yields 2NO2. I can ask you which one, just by looking at the picture, which one is the one that gets used up first. You could see that what you have left over is O2. So that does not get used up first. The other one does. So NO. Alright, so this concept we're going to use in chemistry math problems. So I suggest that you really grasp what this means. Let's do a problem now that deals with limiting reagents. This is example or practice exercise 3.15. It reads, the reaction between aluminum and iron 3 oxide can generate temperatures approaching 3000 degrees Celsius and is used in welding materials or welding metals. Sounds like none of that information I'm going to need. And then they give you a equation or reaction. First thing you got to do is make sure that this reaction is balanced, but it is. You can check it. The actual problem asks you, in one process, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. Calculate the mass in grams of aluminum oxide formed. This is simple, okay? We already know how to do this. Basically, they've given you grams of A, remember from the last video, grams of A, and you've got to take it to grams of B. We know this path, but they give it to you for both reactants. From now on, these problems, you're going to have to figure out which one is the limiting reagent. First thing is, you got to check to make sure that this reaction is balanced. We did that. Second thing is, they want to know how many grams of whatever is made. But before you do that, you got to figure out which one of the reactants gets used up first. They give you the starting grams of both materials. So you've got to take it to the product and figure out which one makes less. So we would take 124 grams of aluminum, which is our A, and then we would take that to moles of A through the molar mass. Once we're in moles of A or moles of aluminum, we would use the mole-to-mole ratio in the balanced equation to get to moles of aluminum oxide. From there, then we would go 2 grams of aluminum oxide through the molar mass, which is 101.96. That gives us 234 grams. Okay, so that's how much grams are made from 124 grams starting material of aluminum. You do the same process for the other guy, 601 grams of iron 3 oxide. If you do the same thing, you notice that you get 383 grams of aluminum oxide. So what I've done here is I've taken 601 grams of iron 3 oxide. I've used the molar mass to get to moles of iron 3 oxide. I use the mole-to-mole ratio to get to aluminum oxide, and then I've used the molar mass to get to grams of aluminum oxide. That gives me 383 grams of aluminum oxide. So what that means is that the limiting reagent of this problem is the aluminum, because you only made 234 grams of that one, and you made 383 grams from the iron oxide. So the one that gets used up first is the smallest one. So you would note that your limiting reagent is the aluminum, and your excess reagent, the one that's left over, is the iron 3 oxide. Okay, so we've answered the question, because calculate the mass in grams of aluminum oxide formed, it must be 234 grams of aluminum oxide. Second part, how much of the excess reagent is left at the end of the reaction? This is very simple. All you got to do is go backwards. But you have to start from your limiting reagent. That makes sense, because how are you going to start from the one that is not used up? You've got to start from the one that was used up first. So you start from 234 grams, right, because that's how much was calculated, and that's the limiting reagent. 234 grams of aluminum oxide. You use the molar mass of aluminum oxide to get 2 moles of aluminum oxide, and then you go back to iron 3 oxide because that was your excess, right? They want to know how much excess is left. So you got to go back to the guy that was the excess, which is the iron 3 oxide. So again, you start with 234 grams of aluminum oxide, you use the molar mass to get 2 moles of aluminum oxide, then you use the mole to mole ratio to get to iron 3 oxide. Then you use the molar mass of iron 3 oxide, which is 159.7 grams, to get to how much grams was actually used of that excess reagent. It was 366.988 grams. But that's not your answer because you started with 601 grams. So you have to subtract what was used. So 601 grams of what you started minus what was used, which was 366.988, will give you 234 grams of iron 3 oxide. This exercise or this type of problem takes a lot of steps, but all these steps you know how to do. It's the same path from the last video. So if you can just get that path down and realize what they're asking you, this is a very simple question. The last section that we're going to discuss is 3.10. It goes over reaction yield. So the amount of limiting reactant that's present at the start of a reaction determines your theoretical yield. Okay, theoretical yield is the amount of product that would result if all of the limiting reagent is actually reacted. Okay, so this is in a perfect world. In a perfect world, everything that you put into a reaction gets used up. But in actuality, that does not happen, okay? Things get dropped or things get evaporated or there's contamination or whatever you want to think. But theoretical yield is, in theory, how much should I get if I put in X amount of grams at this reaction, I should get this amount, okay, on paper. But the actual yield is what you actually get. All right, so that takes into effect, contamination, drops, or recovery, everything. So all you got to do is remember that percent yield is the actual yield, what you actually get, divided by what you should have gotten in a perfect world, your theoretical yield, times 100. That's it. So obviously, percent yields may range from 1% to 100%, and obviously the higher percent yield you have, the better. Right? So, as a chemist, I try to maximize my percent yield in a reaction. That means that reaction is really efficient. Or if I have a reaction that comes out to be 10% yield, not so good. I'm probably going to try to switch the stuff that I'm doing to make it a better percent yield. Lastly, I want you to try this practice exercise because it takes into account everything that we've just learned. It reads, industrially, vanadium metal, which is used in steel alloys, can be obtained by reacting vanadium 5 oxide with calcium at high temperatures. Sounds like I don't need any of that information. But then they give you a reaction, and the first thing you have to do whenever you get a problem is what? Check to see if it's balanced. This one is balanced, so we can move on. In one process, 1.54 times 10 to the third grams of vanadium 5 oxide react with 1.96 times 10 to the third grams of calcium. A. Calculate the theoretical yield of vanadium. For you to answer this problem, you have to find out first which one is the limiting reagent. Once you find out the limiting reagent, you take that amount in grams and figure out the theoretical yield. You cannot do simply one of those starting materials and go to vanadium. You have to figure out which one is the one that gets used up first. So take both of those starting materials to vanadium, figure out which one is the least. That's your limiting reagent. Once you have that, then that's your theoretical yield. That's how much you're supposed to get. From that, then you can calculate the percent yield. And they give you how much vanadium was actually obtained. So you know everything you need to know to do this problem. Good luck.